This is AP Calculus. I'm calling it 6-8 Part 3. We're going to talk about integration of exponential functions. And to talk about exponential functions and their integrals, we have to first remember what it was to take the derivative of an exponential function. Remember that the derivative of e to the x was just e to the x. And the derivative of e to the u, where u is some function of a variable, is u prime. We take the exponent part and take its derivative and then keep the e to the u. So then working backwards, if you have the integral of just plain e to the x dx, then that's just e to the x plus c. Remember, if we have boundaries here and it becomes a definite integral, then you would plug those numbers in. We'll do some of each type today. And then if you have the integral of e to the u du, remember, the du has to be paired with the derivative of the u part, and then it can be integrated to give us just e to the u plus c. And again, sometimes we will have definite integrals and have to plug numbers in to find the actual area under the curve. So here's the first example. This one is pretty straightforward. It's not too bad, but we have to account for this being our u part, and we have to use u-substitution to think about what else needs to be there so that we can take the integral. So I'm going to let u equal 3x plus 1. So du would be the derivative of this, 3 times dx. And so if you look at what we have here, we have the u part, but in here we do not have the 3, and we do have the dx. To be able to integrate this, I need to put that 3 in here. So if I put the 3 in, I've got now 3 dx, which is my du part. And if I put something in here, remember, I have to offset it so that I've only multiplied by 1. Well, what can I multiply by to make the 3 a 1? Well, that would be 1/3. 1/3 times 3 is 1, and that makes it the same as what we started with. It looks different. We haven't changed its value. So if I do this and do my u-substitution, I keep the 1/3 on the outside. That's e to the u. 3 dx is my du. And now this looks just like my integral rule. And so the integration of e to the u du is just e to the u. So I've got the 1/3 e to the u plus c. And then I resubstitute my u back in. So I've got 1/3 e to the 3x plus 1 plus c. In this example, remember, we're going to let the u be the exponent of the e part. So I'm going to let u equal negative x squared. And then du is the derivative of the u. So if I take the derivative of that, I've got negative 2x dx. That is the derivative of the negative x squared. Then I need to go over here and see about substituting in with my u-substitution. Well, notice here, this is a 5. I need that to be a negative 2. So I think probably the easiest thing to do here is just to bring that 5 out. Remember your properties. That 5 can be brought outside. We'll leave the x. Well, you have to leave the x inside. And then I need this to have a negative 2 in front. So I'm going to put the negative 2 in front and then divide by negative 2 on the outside. That's probably the easiest thing to do, rather than trying to figure out what needs to be multiplied on the inside and the outside to force the 5 to be a negative 2. And so now that I've done that, I've added what I needed, added in, and I've offsetted it by dividing on the outside. I can do my u-substitution. So I've got negative 5/2 e to the u, and then negative 2x dx is my du. If I take the integral of that, that would be negative 5/2 e to the u plus c, and then I just resubstitute. So I've got negative 5/2 e to the negative x squared plus c. And you could take the derivative of that, and when you do, you should end up with what you started with. For the next one, this one the u part, again, is what the exponent is. So I'm going to let u equal 1 over x. And then to find du, it would be easier to think of it as x to the negative 1. It would be negative x to the negative 2 dx, which is the same thing as negative 1 over x squared dx. Well, if you look at what we've got here, we have a 1 over x squared, but it needs to be a negative 1 over x squared. So I'm going to add in a negative 1, which means I just put a negative in front. To offset the negative in front, I need to put 1 on the outside so that I've made the problem look different, but I haven't changed its value. Then I'm going to do my u-substitution. That would be e to the u, and then negative 1 over x squared dx is my du. Then I integrate. When I integrate e to the u, I just get e to the u plus c, and then I would resubstitute. That's negative e to the 1 over x plus c. And again, you could take the derivative of that to make sure it matches what you started with. For this one, I've got e to the u. I'm going to let u equal cosine x. So du is the derivative of cosine x. Well, the derivative of cosine is negative sine. So that's negative sine x dx. I have the sine x, I have the dx, I need the negative. So I'm going to tag a negative in front, and I'll set it with a negative on the outside to make sure I haven't changed the value of the problem. Then I'm going to do u substitution. So I've got negative times the integral e to the u du. When I take the integral, I have negative e to the u plus c. And then if I resubstitute, I have negative e to the cosine x plus c. This one is a definite integral. So now we're going to take the integral using u substitution, and then we'll plug in the a and b to find the actual answer. With this one, my u is going to be the negative x. My du is going to be negative dx. So in order to have my du in there, I need a negative tagged in front. If I put 1 in the front there, I need to put 1 on the outside to offset it so that I haven't changed the value of my problem. So I have negative going from 0 to 1 of e to the u du. The integration of that is a negative e to the u. We're going from 0 to 1. We don't need a plus c this time because they did give us boundaries at a and b. We resubstitute with what u equals, so that's negative e to the negative x, going from 0 to 1. When we do definite integrals, we plug the top number in first, so we have a negative e to the negative 1 minus a negative e to the negative 1 times 0 is 0. Negative e to the negative 1 is the same thing as negative 1 over e. That would be a plus 1. And that would be our final answer. It still has an e in it. Most of the time when you have e's and it's a definite integral, you're going to have some e's left inside. That's okay. Sometimes you won't, but most of the time you will. Here I have cosine e to the x dx. So this one's a little bit different. We're still using the e to the x notion that the integral of e to the x is e to the x, but this one's a little different in that it's got that cosine. And remember, when we're taking the antiderivative of a cosine, most of the time we let our u be the inside part. And if you look at what happens here, if I let u be the inside part of that trig function, e to the x, then wouldn't du be e to the x dx? So we have the u and we have the du already available to us. There's no multiplication that we need to offset anything. This one is pretty straightforward. It just is a little bit different where normally with an e function, the u part is this part, but in this case, it's a little bit different. So you sometimes have to really look at the problem to determine what your u part is. Just because there's an e in there does not necessarily mean that every single u value is going to be the x part or the exponent of that exponential. So just pay attention to that as you're doing these. This happens most of the time with trig functions. So I wanted to make sure I showed you this. So the integral from -1 to 0 of cosine u du And then the antiderivative of cosine is sine. So we have sine of u from -1 to 0. We will resubstitute. That's sine of e to the x going from -1 to 0. And so then if we plug in the top, we have sine of e to the 0 minus sine of e to the -1. And we can rewrite that as sine 1 minus sine of 1 over e. You could plug that in the calculator and get a decimal. I tend to just leave it like this unless they ask me to solve it further. I usually just leave it like this. This is an exact answer. If you get a decimal, you have to round. It's no longer exact. So I tend to like the exact answers if I can use that. Here is another definite integral. Go ahead and copy that down. See if you can do it on your own, and then I'll come back and give you the answer in a minute or two. For this one, I let u equal the -x squared. So the derivative of -x squared is -2x dx. Then I did u-substitution. I had the x, but I did not have the -2 in front. So I put the -2 in front. I'll set it with a -1/2 outside so that I've only multiplied by 1. Then I do u-substitution. That's e to the u du with that -1/2 still outside. The antiderivative of e to the u is e to the u. Then I resubstitute and make the u back to the -x squared. Then I do my substitution of my a and b. So I plug the top one in first, leaving me with -1/2 e to the -1, which is -1 over 2e. And then when I plug in 0, I have -1/2 times e to the 0, which is just 1, minus a negative would be a +1/2, giving me my final answer of -1 over 2e plus 1/2.